sword, and I start, I tell all the other players that sword is now gone. So you can have a race condition for that.
Yeah.
And we just sort of arbitrate it, the level master gets to make the determination of who actually got that.
So basically, two people, in their separate copies of this game, they both go to pick up the sword, right? And they both think that they picked up the sword, so they send out the packet, I picked up the sword.
Well, more like I am attempting to pick up the sword.
Okay, so there's actually a two-stage process. I'm attempting to pick up the sword. Particular nuance to that, or it's like doesn't really matter?
No, it's pretty straightforward. It's whoever got it first, and of course, if you're a level master, you're obviously faster.
Is this the microphone? Yes.
Good. Okay, and so is that roughly the way that most things in the game work? So if I try to attack somebody, is it a similar two-stage process? I'm trying to attack this person, and then the level master acknowledges it, and only once he acknowledges it do I actually see the attack occur? Or is it more asynchronous than that, in that I see the attack occur either way, but maybe the damage goes back up later if it turns out it didn't acknowledge it? You know what I'm saying? Like in terms of how does that work out when we're actually doing other sorts of things besides something as discrete as picking up the sword?
Right, so it's really loose. So you go and attack a monster on your system, and you kill him, and you decide that he's dead, and then you let me know that he's dead,
okay.
And I'm the level master, and I go, okay, great.
Okay.
Yeah. So, I mean, it's really possible to cheat very easily, right? You can just kill anything as fast as you want.
And that isn't really, but I mean, ignoring the cheating part of it, in terms of actually keeping the stuff working in the actual game, it's not really necessary to do anything beyond that. Meaning, if a bunch of people who are all trying to play the game, legitimately not hacking it, not trying to do anything weird, then simply having the clients announce when they did something, and if two people say that they killed the monster, it doesn't matter because the state just goes to dead, and so it's fine. That kind of thing.
Right. The only area of contention is in picking up things off the ground.
Okay.
Or breaking open a chest. Actually, no, even that doesn't, because the chest is broken open. Both players might have done it at the same time, but it leads to things popping out on the ground that you can then pick up that are the areas that you fight over.
So the only, is that because things like damage are just numbers that go down? So if I get two people who say they did damage, I just apply them both? Or is that just because picking up is the one thing where it's there was only one item and we need to know who had it kind of a thing?
Exactly.
Okay. All right, so I think that's pretty good fundamentals. I'm trying to think if I missed anything of these or
don't do a game like this.
Okay, why not?
Because people will cheat.
Okay.
And in fact, the thing that happened was, Diablo came out and people really loved the game, and a lot of players had fun, particularly when they played with their own friends. But as soon as you played out there in the larger universe, there were just lots of people who were griefing. And in fact, it was really startling to me because, I'd played MUDs before and things like that, and occasionally there was griefing, but usually you had GMs who would oversee things, volunteer GMs, who would sort of instant assholes.
Right.
But so a couple days after we shipped Diablo, there was a friend of the company who came in, and he was playing in an office basically, a guy named Josh, and he's just going to dungeons and he's killing people because he's higher level than them. There's nothing they can do about it, and so all their armor and swords and everything pop off onto the ground, and then they get reincarnated in town, and they come down in the dungeon naked and trying to recover their stuff, and he kills them again, and again, and
this
again.
was at your own company.
And he taunts them. Well, he was actually just a friend of somebody who worked.
Oh, okay, just a friend. Okay.
And I was I watched him, and I realized that this was a microcosm of stuff that was going to happen.
Right.
So I didn't say I didn't say you shouldn't do this or anything like that. Instead, I was let me understand this, and that's really my first serious experience with griefers. And it was shocking at that time. And now, every game I've ever designed since, I have to think about how are people going to hack this, and how are people going to, especially abuse others, which is in some ways even worse than hacking.
Yeah. Well, okay, so that's actually kind of fascinating. So moving forward, I guess the next one we did was Guild Wars, yes?
StarCraft and Guild Wars.
Okay, so you did the difference in StarCraft as well.
Yeah, it was a lot of the same.
Was that asynchronous or was that synchronous? Was that more like the Warcraft model?
Just like Warcraft 2.
Okay, just like Warcraft 2. Okay, so after StarCraft, you go to start Guild Wars, and I remember Guild Wars was particularly impressive to me because I remember the download Guild Wars was this little tiny thing, right? There was some kind of little tiny executable, and it just took care of everything from there and all this sorts of stuff.
That's right. It was a 200K executable.
200K.
And so the challenge was that it was so small that people would click on it to download, and it would go so fast they'd be like, did that work? So I think we should have made it bigger.
We got to pad it out just to make sure they could see the progress bar.
That's right.
So Guild Wars is, in some ways, a lot more ambitious than Diablo because this now is sort of designed up front to have a lot of the permanence maybe backed up by or authenticated sorts of things, I guess. This comes out of your experience with the griefing on Diablo, I guess. Is that would that
That's
be
right.
fair?
And also the desire to have an online economy.
Okay. So this one, I guess, well, I got kind of a list of things to drill down in here, but before I maybe ask any of those questions, can you give maybe people a brief understanding of what was involved in making Guild Wars happen? Because it's got both a persistent state and it's got a peer-to-peer thing happening, and those things interact. And there's just, I remember you sent me an email where you're like, here's all the servers we wrote for Guild Wars, and there was like 12 or something on this list. So can you just give a brief, just high-level explanation of what was involved in just the basic architecture of this?
Sure. So first, it was not a peer-to-peer game at all. It was a client server only. So
so even when people were playing inside their own, when they would kind of spawn off the dungeon, that was still always round-tripped through a separate server.
That's right.
Okay, sorry.
Fully server hosted. So the very first thing you do is you connect up to the server and say, hi, I'm Guild Wars version 0, because you've got this 200K stub. And it's like, oh, you need version 53. Here you go. Download, you reboot the game engine. Okay, I'm version 53. What should I get? Okay, great. You're up to date. Here's the manifests for every single piece of data in the whole world.
Okay.
And you download that file, and then you say, well, I want to go to the login screen. Give me all the files I need for that. And you download those, and progressively you start accumulating all the files you need, so that you never actually have to download the entire, roughly at that point, 3 gigabytes of data. You could just download the tiny portion you need.
So this was actually sort of like an on-demand package manager you basically had in there, which is like,
right.
We have a dependency system. We know everything in the world and what it depends on. So when the game starts up, it just kind of asks for some kind of like a root object for what it's trying to do. Like, I'm trying to go into this dungeon, so I need, I ask for that. And then it starts pulling in things, and you're like, okay, now I'm going to ask for this, and that pulls in more things. These get downloaded into sort of a cache on the drive?
That's right.
Keep? Okay. And those are marked in some way to tell whether they're stale in case they're updated, or does that never happen?
Every file effectively is an ID number, but there's both the identity for it and the version number.
Okay.
And so you can know whether you're up to date on the file. And so if it turns out that you're out of date, you can say, I have version 17 of the warrior armor, and it goes, oh, and if you look at the manifest, it's like, oh, I need version 19. So you say to the file server, want 19, have 17, and it loads up both those files, Delta compresses them.
Seriously?
Well, actually, Deltas them, then it compresses them and sends you down that small chunk, because this was 2005 when we were doing this. Actually, 2002 when we were writing the code for it. And bandwidth was much lower than it is today, so we had to make everything as small as possible. Otherwise, it would have been hours and hours before you could get into the game.
That's awesome. Okay, so you on-demand delta compress the difference between the version they have and the version they need, and send only the delta down.
Correct.
That's like better than most internet infrastructure probably is everywhere in the world right now, but okay. Going back to sort of that sort of process of doing things,
right.
You said the ID number and you said it's both the ID and the version. You mean they're together, or the ID is somehow intermixed with the version? It's just two separate pieces of data, ID and version, or
that's right. So every file has a base ID, which is the very first file number that was assigned to it when the asset was created. Okay. So I create a texture. It's like, well, you just have to be number 3, right? And so I can forevermore I can refer to that texture as 3, but now it has different version numbers. So
I have a burrito.
File 17 and file 28. Every time the artist changes it, that texture gets a number with it. And so I always refer to it by the base ID, and I look in the manifest for it, and it's like, for the base ID 3, the current version is 781. And then I say, I need 781, I have 3 or 17 or whatever the previous one.
And so, sorry, this is just kind of fascinating. So sorry, this is not technical. That was
my life, so I'm
just... okay. And just one other question about that, I guess, because we sort of talked about this with when we were talking about Super Meat Boy as well, and what Tommy was doing, and it's just kind of fresh in my head. Like, how do you assign these IDs to things that artists make? Because by definition, an artist is not somebody who goes and knows what a Mace ID necessarily is. So how does that process work? I'm somebody who needs to add a texture to Guild Wars. Is there a server that you query, or their tool? Like, just give me just a quick idea of what that looks like.
So we're using Perforce as our revision control system. Okay. So they check the file under Perforce, and then there'd be some way that file was referenced. So perhaps there's a model file.
Okay.
And the model file, using 3ds Max refers to this texture file by name.
Okay.
And so, and then that model file is referenced in a level file.
Okay.
Say it's a tree since that seems to be the model for today. And then the level file contains a bunch of different assets in it. And then the level file is actually referenced in some source code. Like this is level 13 of the game, or this is like the Lion's Arch outpost.
Okay.
And so what happens is there's a tool, FS build, that goes through and it picks up all the code references to assets. And it's like, okay, let me load this level file, and then let me look at the dependencies it has. Oh, it's got a model file in it. Let me load the model file. Let me look at all the dependencies. Oh, it's got a texture file. Let me load that. Oh, textures don't have any dependencies. Okay, so now I can process that file. That file is now file ID 3 because it's the third file that's ever processed.
Okay, and that whole stack gets processed up into the piece of data that's actually referenced?
That's right.
So the textures aren't referenced separately, or they are?
They can be referenced separately. That's right. So it processes and saves file ID 3 in this big giant, data. Well, you can think of it as a database of files that has like more or less every version of a file back, say, 90 days or something.
Okay. And so when you're doing that, how can you tell that I'm an artist, I made a new version of this texture? How does it correlate those? Does it just use the path, the full file path in
Okay, we're getting
Vertex
started.
as the thing that it knows it's seen this before? So that thing kind of tracks those and can associate the IDs internally with that Perforce path? Or?
Oh, that's right. So FS build loads up all the assets and creates this graph of everything. And then he goes, oh, well, that file hasn't changed. I don't have to do anything for it, right? So because it has lots of metadata associated with the process, so it knows when
Go lay down.
And if something breaks, it knows which artist to check that file in.
Oh.
Cool. That is Handmade Con, by the way. And all the interviews are really interesting. There are like 6. I'm only on the 3rd one. This guy's a network programmer, and he's freaking amazing. And Mike Acton was really good too. Okay. So, where we left off on the last stream was, by the way, this stream, okay, this is the Math for Game Developers stream. And let's take a look at that real quick. This is my YouTube channel. And we have a bunch of videos that explain how, oh, you're also seeing my private videos. Dog videos. So it's a series on how to, that teaches math for game developers. It is what it sounds like. And hey, Jan. How you doing? And so this is a stream where I'm developing these videos and teaching math and making the videos and doing some programming too. And so where we ended up last time was here. The sample project that we have that we do all the implementation of our math in was broken, but I've gotten it working now. All right, here we are. It's a simple math playground right here. And it took me hours to figure out what it was. It would have been really boring to stream, so I'm glad I did that off stream. But I would like to explain what was wrong. So there were a few things wrong, because I feel like that's pretty instructive. Okay, so thing number 1 that was wrong is that in new OpenGL, everything has to be in a vertex array. What is a vertex array? So actually, before I explain what a vertex array, I'll explain what a vertex buffer object is, and that's what I'm doing here. I bind a vertex buffer object, and then you add the meshes that you're trying to render to the buffer object, a VBO, vertex buffer object, and then you tell OpenGL just render. So a better way to explain it is that the VBO is like a name for a bunch of meshes that you want to render, and it's required to have a VBO for anything that you want to render these days, whereas like before it wasn't. So I was using some old code where you could like you could just send a mesh to the video card and say, hey, render that mesh. But now you have to load it into a vertex buffer object. And then a vertex array is like it's the vertex buffer object and then a bunch of properties of the vertex buffer object that you can see here. Like it has these attributes and these, and then you have to specify a bunch of offsets into the mesh for each of the attributes. That may or may not make sense depending on how much OpenGL you've done, but that's what was wrong, is that I was using the old way of doing things, and so now it works. Now it's the new way, and it works, and it's pretty again. And I'm gonna have the, like, if you care, I'm gonna have the diffs for how I was able to fix it. That's going up in the source repository that everything else goes up in. So if you want to see what I did wrong, that will all be there. So where we stand right now is we can start integrating. My fan is running because I'm running this thing in the background. My fan is starting to run, so I'm gonna stop it. We're gonna start to integrate the last week we did. Oh, I'm so bad with names. Fixed point iteration. Not quite double action 2. Last week we did fixed point iteration, and we were going to Blue Ocean. We were going to integrate let me load it up on YouTube. Let's do this. Blue Ocean. We used fixed point iteration to do the simulation for the vines that you see in this video, the physics simulation for these vines. So we were going to integrate that physics simulation into our little test project, and then record the code section of the video. So let's do that. Where am I? Quit this. Do I have a copy of the Blue Ocean stuff on my hard drive? No, I don't. So let's first download that. And this is a Windows only project. I never ported it to Mac, but that's fine because we're just gonna rip out the guts and add it to our, the Math for Game Developers project. So good, now here it is. Let me actually open it up in the Finder. And where is it? Here it is. So it was the Seaweed. So let's open that up. All right. So most of this can probably just be copied directly over, actually. The rendering of the Seaweed I did like in bare OpenGL, but we can probably deal with that somehow. What other source files will I need from here? All of that was in a header, which would normally be kind of weird, but this project was kind of janky. I didn't really do any quality engineering on it. Let's just open up the whole thing. Why not? We'll drag the whole thing over here. And wow, okay. And I'm just gonna close each file as I determine that there's no references to the Seaweed in it. Close that one. Close that one. This one has Seaweed, so we'll keep this one. What is this? Oh, I have too many files. I can't even read the file names. Yeah, so this is the main file. Okay. So I probably need some stuff from here. That's the main file of the blue ocean. Okay, there's not going to be anything in either of the Boyd's files or in the butterfly fish files, and this is a shader, so that will be boring. And that is the seabed height map. So that's boring. Okay, that's just a bunch of math. That just looks like some data. For this project, I did something really weird. I didn't want to like load any, I didn't want to include any of the code to load any files. So instead, I wrote an exporter. So I took like my model from Silo or whatever 3D program, I forgot, I think it was Silo. And I wrote an exporter to write code that contains all of the vertices of the model in like an array. And here it is, a gigantic array that contains all of the vertices of whatever it is. I think it's the ocean floor. And so instead of like parsing a model file, I just open this array and pass it into OpenGL. And that's super fast to do the actual loading into OpenGL, but slow, like to actually load the program into memory is slow. So you gotta, like, nothing's free. You gotta pay for it one way or another. You either load the file from the hard drive, like a model file, or you load the actual binary that has all this data in it. All right, so, and then we have seagrass. Seagrass we don't care about. So seagrass is all of these things right here, and we don't care about those. Seagrass is pretty boring. So that's to render a blade of seagrass, I think. Oh no, this renders a whole patch of seagrass. And that's boring. So, what else in the file? Okay, so here's the simulation step, that's fine. And there's a render step. Okay, pretty simple. So this looks like it initializes the seagrass, the seaweed, so we're gonna need that. There's an initialization step, a simulate step, and a render step. All right, and then we have the actual seaweed code. So let's first just copy the seaweed.h file over to our math project. New Finder window. Okay. Copy. Paste. All right. And then open the version that I just copied. Maybe this is a bad place for it. Let's put it up here. All right. Okay. So first let's do the initialization. This looks like a good function because it's the load function. So we want to do some kind of loading. All right. There's some kind of global, and no, I don't normally use globals, but since this is just, I'm not worried about quality engineering, I'm just gonna do a simple global. Where is it? It's gotta be defined somewhere. Oh, of course it's defined in the header file. Yeah, okay, that's fine. Then I should say include seaweed. All right, so that will get us that global. So we have to, let's see, for each stalk of seaweed, this line of code is way too freaking long. So the first two positions. Oh, yeah. So it just sets. So these are the initial Seaweed positions. See, it says get seabed height. So we're not going to do get seabed height because in our little silly test level, everything is the same height. Everything is the same height. It's all flat. So we can just make this a little simpler by saying 0. 0 should be the height of the floor. And then from there, it sets the position of the next link to just be, yep, one link length higher. So far, so good. Now we have to do some kind of simulation step. Where are we going to do that? Update. Update sounds like a good function to do a simulation step. Let's go to the bottom of the update function, stick that right in there. Do these globals get initialized? Yes, they do. Okay, I made this really easy. Alright, then where's the render step? Oh, wait. Render Seaweed. Just gotta call the render Seaweed function. Simple. Wait, it's called draw here. Draw. So then at the end of the render step, okay, let's just squeeze it right in there. So this is weird since I use this clever little library that I wrote to abstract away all the OpenGL stuff so that I don't have to do direct OpenGL calls. But the render Seaweed function does make direct OpenGL calls, including shaders. So now I have to make the decision of, do I want to, oh yeah, and see here I use some sphere data. Somewhere else I must have set up a sphere. Okay, so I'm gonna have to do something weird. I could make it into a box. I know how to render boxes. Yeah, I think I could probably rewrite this code pretty easily because I'll just render it with boxes instead of spheres. For now, anyway. Okay, so let's see. Oh my goodness. I am going to have a lot of compile errors. This is going to be fun. Watch this. So I use vec3 in this code, in the Seaweed code, and vec2. I'm like vec3, vec2, but in the math code I just use like capital vector. Here's what we'll do. Define vec3 vector. Define vec2 vector 2d. I think those are the names that I use in the math playground. So that should fix a lot of this stuff. And yeah, actually, we have many fewer errors now. But we do have some differences in dot product. I'm just going to define a quick function right here. Inline float dot. It takes a vec3 and a vec3, and we know what dot product does. Return a dot x times b dot x plus a dot y times b dot y plus a dot z times b dot z. All right, so now we've made a dot product function in the way that this file expects. Oh, interesting. So it wants an operator overload that takes a vector 2D to a vector 2D. We can do that. We can do that. Inline. Okay, so what happens when you multiply two vectors? Ha, nothing. Like, strictly in mathematics, multiplying two vectors is an undefined operation. But a lot of people in their vector classes define it to be a component-wise multiplication. So a times a, and then it. Or here, I'll just write it. So we need to have a vec2, and we're going to do operator times, and then vec2a and vec2b. So we're just going to return it, and we're going to do component-wise. Yeah, so this isn't like strictly kosher mathematically, but it's really convenient for, let's look at the line of code that's doing it. If you have a vector that is, for example, a color, and it's this line down here. Let's see here. Maybe we can find a better example. No, not really. So I'll just write an example up here. If you have a color, some kind of color, and then you have let's do this. You have the diffuse. Yeah, we'll do it like this. And the specular. Components of a shader. And then the combined is, diffuse times specular. And this is what you want. You want like component-wise multiplication, because physically that's what happens. The diffuse component and the specular component get multiplied together like that. And hopefully that made sense. If you've seen my shaders videos, then that will probably make some sense. But otherwise, it might not make very much sense. But that's okay, because we're just trying to get this to compile. What else is going on here? Let's do another compile and see. What? I just defined dot. I only defined it for 2D. For 3D, so let's define it for 2D as well. And it's the same, you just don't have a Z. Oops. Okay, why is this complaining? Because it wants another operator overload, but this time it wants float. And so this result is just going to be piecewise multiplication like we do in, I think, the second video or something like that. All right. So now the simulation time is undefined. That's because we need to use the simulation time that is provided to us by the Math for Game Developers framework. And where can we find that? It's this. Wait. No, it's not. Ooh, where can we find that? That's probably it. So let's drop that in here. All right. Player position, that's a good thing to know. So the way I programmed the Seaweed is they will react to the player, and we want to keep that. We want to keep that like reacting, if the player gets close, he'll push the seaweed away. And you saw it in the video, the reeds would like get out of the way. So that's what that is used for, to calculate the amount of force to apply to the thing based on where the player is. So let's see if we can, oh, there it is right there. Player get global origin. We'll just drop that in there. And, oh wait, that's a local. Okay, you know what we'll have to do then? Game. Oops. Okay, that will probably work. Looks like it worked. Nope, it didn't work. Ah, MH player is a private member of C game. That is because I'm using too much C++ here. Following the lead of our good friend Casey, I only rarely use private anymore. So I'm just gonna change it to public. If you've not watched any of the Handmade Hero videos or heard Casey talk about his opinions on object-oriented programming, it's good stuff. I recommend it. So now we want a length square operation given a, what kind of vector? That's probably a 3D vector. And that is just that, as covered in one of my videos. So same thing for normalize. So for this guy, we have to do that. I just know I'm going to get one of these wrong. It's going to be awesome. Okay, we want a length. And that's this. You guys are going to check my math on this, right? Make sure I'm writing the right functions here. What? Oh. Get seabed height. We agreed that that would be 0 from now on. And, oh. No. No, it doesn't. What? So this is my trick that I was using before to, thank you, Jan, to detect if it's an NaN and not a number. But the compiler doesn't like it for some reason. Oh yeah. Oh, I must have an operator overload in there. Okay, let's write one. Inline bool operator not equal to, and let's see, we have a vec3a and a vec3b, and so that will be, oh weird, I'm gonna write the inverse and then negate it. So the inverse is whether they're equal, so that is a.x equals b.x, and a.y equals b.y, and a.z equals b.z. Okay, and now that I can see that, you apply De Morgan's laws, and if you wanted to write it the not negated way, which is equivalent, you would do a.x not equal to b.x, or a, and so on. So the ands turned into ors, and the equals turn into not equals. It's weird. Logic, you can't just like distribute logic across ands and ors without reversing everything. So that should do that. And what else do we have to do? Oh, we want to get a vector for the direction the camera is facing. Well, we have that. Here it is right here. Use of undeclared identifier max. C is weird. So I actually defined one called vmax. That should be defined. Yep, it's ambiguous though. Okay, we want the float version. Oh wait. Looks like I didn't define a floating point version. That's interesting. Let's go define one. Done. Okay. See, this was a Windows project, and _debug break is a Windows specific compiler intrinsic that breaks you into the debugger. But I have, let's see, debug break. I think I have that should work. Yeah, I have a function that does that more cross-platform wise, so we're going to use that instead. What does G-splining mean? Oh, right. Yeah, no, we're never splining. In the original video, a spline is used as the camera path, but we're not going to lock the camera to a path anymore. And G-splining just tracks whether I'm like in debug view and I can fly around wherever I want, or whether the camera is locked to the splining path. So in this case, the camera is never locked to the splining path. Okay, now we have to decide. Okay, it looks like we've gotten past a lot of the math stuff. So let's start by, let's see here. Let's pass in a render context into this function. Okay. A render context or a rendering context? A rendering context. C rendering context R is what we will call it. So now we can use this new render context to set up the shaders and stuff that we want to do all the drawing. We will use the model shader that we got for free from the math part of things, from the math framework. So now let's see. This stuff is boring. Set color. Set color. What does that do? That must set the color for this program. So the way we do that in our math program is like this. I think. This is weird though. What's it doing? This doesn't look like. There are 3 colors here. Why are there 3 colors? Now I have to know what that thing is doing. So let's go over to that project. It doesn't look like it's setting 3 colors instead of 1 color. I don't know why it would do that. So grep set color, and I always forget to write -R for recursive. So we got a bunch of places here, but where is it defined? It's defined right there in anim.cpp, which I just closed. No, it's still open. So void set color. Right. So, right. It's setting the color for a bunch of different parameters. Yeah, but we only want to set one color. Okay. So wait, which one is the one we want to keep? The second one is diffuse, and that's the one we want to keep. So here's the first one. We'll get rid of that. Here's the second one. We'll keep that. Here's the third one. We'll get rid of that. All right. So now we have set the color. So now we're going to create a matrix that we're going to use later to render the thing. And as a scaling matrix, let's see, that probably won't compile. Oh. This is a pointer. I guess we got to do the same thing we did before for matrix. Define mat4 matrix 4x4. Okay. So this just creates a scaling matrix. And I have a function that does that for my matrix library. So let's use that. Where was I? Where was I? Here. That should do it. Okay. Gotta define mtau. That's easy. Mtau equals, or is 2 times mpi. So tau is kind of a silly thing. We all know what pi is. Pi is the ratio of a circle's diameter to its circumference. But some mathematicians have decided that the ratio of a circle's radius to its circumference is the more fundamental number. So instead of 3.14151, they think that 6.283 is a more important number than pi. So, but tau is really just 2 pi, like the radius is half of the circumference. So that's what tau is. In fact, I find it easier to think in terms of tau than in terms of pi anyway, because if you think about it in terms of tau, tau is a complete trip around the circle. It's literally the circumference of a unit circle, whereas pi is half of the circumference of a unit circle. So if you're talking about like sine of tau is 0. Because if you go all the way around the circle, your y-coordinate is 0. And then if you have sine of tau over 2, then you've gone halfway around the circle. If you have sine of tau over 4, you've gone a quarter way around the circle, and so on. Whereas if you do it in terms of pi, like pi over 2 is a quarter way around the circle, it's harder to remember like that. So a lot of times I think in terms of tau. It is kind of handy. Anyway, tau distraction. Transposed translate. What the hell is transposed? Oh, it has to transpose it because, yeah. I don't think we're gonna have to transpose it. Let's go look at what that transpose translate thing does real quick. Maths. like how I called it maths with an S. Here it is. Really? It's not there. It must be... Transpose, translate, grep. Oh. All right. No, that makes it much more clear what it does. Yeah. Yep. Okay. So it just creates a translation matrix out of this vector, except that the way that OpenGL expects the data is opposite from the way that this, whatever this library is. What library is this? I don't even know what library this is. This is not my library. Oh, it's the Angle library. Yeah, okay. So this is some 3D math package, and the way they store their 4x4 matrices is by using 4 vector 4s, and then like you can see the way it constructs transpose translate. The way it constructs the translation matrix is by putting the entries in the last, like oh my god, I can't even think. Okay, so this gets the last vector in the matrix, and this gets the first, second, and third entries, and it assigns it, right? So it's using like it's putting all of these items. Wait, is that right? Yeah, that's right. No, it's not doing anything crazy. Yeah. So it's organized. Okay. Here's the long and short of it. It's organizing the data in memory in one way by putting vectors with adjacent entries. So one vector XYZ comes first, and then the next vector XYZ comes next. Whereas the way OpenGL expects it, it expects you to have all of the vector X's first, and then all the vector Y's next, and so on. And so, is that true though? I thought OpenGL expects it the other way around. But in any case, it has to transpose the matrix before it turns, because it's stored in a way opposite the way OpenGL is expecting it. That is weird. So I don't think we have to worry about that, because we're just gonna take this. Okay, what is it? We're going to make a new matrix. We're going to say m dot set translation. We'll pass it what's in here. Oh, and then it multiplies it by the scale. So I'm actually going to scale it right there, and then pass in the matrix. that should be okay. Need some more parentheses here. Because I think, if I remember correctly, in my matrix library that I wrote for Math for Game Developers, it stores it in exactly the format that OpenGL expects it, and you don't need to do that transpose. I'm pretty sure that's the case. If it's not the case, we're going to find out because our shit is going to look really weird. Okay. So... oh, and then it uses some OpenGL stuff here where I need to set, instead, I need to do set uniform, and, probably this. And then I need to do no, I can just do this. Okay, so I'm using our context instead of the raw OpenGL call. And then I'm going to draw a box. I'm pretty sure there's a way to draw a box. Render box. Render box. We'll use this nice render box function. Render box, and I don't know. I don't know what this is going to have to be, so we're just going to make. All right. So now, so what we just did is we finished the drawing of these balls that sit there in every link in the chain. All right. So now next is the links. And this should be a little bit faster since we already did a lot of this stuff. We can just do another set scale here with different parameters. And then, is everything else good? Oh yeah, vec4, all right. Define vec4, vector 4D. And I missed a parentheses. And we don't have a cross product, seriously? Okay. Let's write a cross product. This is all good review, huh? In fact, since I don't really want to do this again, done this so many times in my life, we will just copy it. Oh, seriously? Okay. XYZZY, that is the name of the game. That should do it. Okay. What? I just made it. I just made cross. Why is it not seeing it? Next link. Oh. Why am I doing it with vec4s? Weird. Okay, well, I can deal with that. So probably, so cross product doesn't actually exist with vec4s. With four-dimensional vectors, cross product is a is like a three-dimensional space only sort of thing. But in this case, they probably are doing homogeneous coordinates, which means the fourth point, the fourth coordinate is always 1. I think that's right. For points, it's 1, and for vectors, it's 0. Yes, because you can add 2 vectors, but you can't add 2 points. Yeah. So we'll just set the fourth value to 1 there, and now that should work. Yes, I didn't use GLM for the math for this structure, for the math for game developers example structure, because I wanted to be able to write everything from scratch, like to go into each math function and rewrite it and say, okay, like this is our cross product function. You know, we did a video on it a while ago. It's x, y, z, z, y. Let's write it ourselves to see that it's really not that mysterious. If I just use GLM, then, you know, it like, you know, you can't go in there and mess with GLM stuff, or at least someone's already written it, and then it's, you know, it's not as fun for us. So I obviously already have these functions. Like, here's the video I did in cross product, and here's the implementation, the x, y, z, z, y. But just to get it working for this file, we're kind of doing a little bit of duplication. If this were my job, I would not write it like this. If somebody were paying money for me to do this, but let's see. But we're just trying to get this working, so we can demonstrate some math. So I'm not as worried about it. What do you mean that GLM is just a basic wrapper? Okay. No matching constructor for initialization. Oh. 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 All right, well, that's easy to fix. Let's write one. It's a $sign. You mean courses teaching OpenGL 3.3? Yeah, it's a good library. It's deserving of its popularity. It predates my own I wrote my vector library before it existed, which means that where's my metric stuff? Which means that I never got a chance to use it because I already have everything in my vector library. But you know, these days, if I were starting today, I probably wouldn't write one. I would just use something like GLM. Where's my matrix stuff? Matrix.cpp. All right. For D. And we don't need this. Will that work? All right. Oh. Oh, give me a break. give me a break. All right, let's make another dot product for 4-dimensional vectors. A dot z times b dot z plus a dot w times b dot w. Invalid operands to binary expression. What? Oh, I don't have a... Oh. So I don't have a division operator, apparently, for 4D vectors. Do I have a multiplication operator? No. Let's do it this way. So I don't want to go write one. So we'll just return vec4, and then we'll do it by ourselves. A dot x times s. And then w is w, w. Fat fingered today. There's z, and there's y. All right, moving right along. Yeah, I thought this would be easier. I guess I was wrong. Oh, and it wants a negative operator for a vector 4D. All right. We'll make a negative operator in line. Vec4, operator minus, takes a vec4, returns another vec4, just negative b dot x. Negative b dot y. Oops. Why did I start writing b's all of a sudden? I don't know. All right. All right. Back to this transpose translate stuff. We should just be able to take the guts and spit it into here. But we actually have to use our render context that we have and then render a nice box. And then, okay, that is almost it. We're down to one error. One compile error anyway. And we just have to use the actual game time instead of this. Okay. So we're probably gonna, I typed wrong components in the next, yeah, probably. Where was that? Thank you. X, Y, Z, W. I knew I was gonna get one of them wrong. I knew it. And, oh, for real? I thought we were done. Yeah, see, now it's gone to compile the next file. So we get more errors. Do I not have a 4D? Oh, I don't. Dumb. Okay. I guess I gotta write one. Well, this is boring. All right. We just need new versions of these guys and set translation wherever he is that take a 4D vector. 4D. 40, 40. And set translation 4D. And then set forward vector. So we copy these guys. For D, and then yeah, I don't think I actually have to do anything different here. For D, everything else should be the same. That's weird. So it's not recognizing the set trans. Oh, because there's add translation. I want set translation. And there. Set translation. Oh, it compiled. All right, now let's run it. It will probably look all goofed up. But that will be an adventure. And yeah, it didn't run. Okay, what went wrong here? This is an invalid uniform vec color. So what should it be? Vec color, that's right. Oh, you know what? What's probably wrong is that I need to pass it a vector 4 instead of a vector 3. OpenGL is picky about that. So let's go to the, you can close this, can close this, can close this. Seaweed, probably can close that too. And yeah, see, we're passing it a vec 3. Let's pass it a vec 4. Is that the only place I do that? Yes. Okay. Let's try it again. And it's still complaining. It is still passing a vec 3. I didn't tell you to pass a vec 3. I told you to pass a vec 4. Did I recompile it properly? It's not doing a recompile when I press my Command B. I don't know why not. Where? Okay. Let's change this file. There we go. Now it picked it up. And what? More errors? Oh. No, vector 4 doesn't have any of the damn overrides. Okay, we'll do it like this. This is the hacky way. I hope that I can convert a vec 3 into a vec 4, can I? It appears so. And it still didn't like it. What? $5.15. Yeah, it's still using the 3D vector version. Oh. Oh. It's because I need that. Didn't actually make it a 4D vector, did I? I just converted it from a 3D vector to a 3D vector. Alright. That's different. now it can't find the uniform for vec global. That's because it's not called vec global, it's called m global. I probably do that elsewhere. I do. M global is the correct name. And it didn't recompile it. This is makefile, not recompiling my things when I build them. Ooh, okay. There we go. So it runs, but I don't see any seaweeds, which is interesting. So let's see what's going on. Actually, render seaweed. All right, so we're stepping through the render seaweed function now. It should find the shader okay. I don't see why it wouldn't. And yeah, the shader is not a null pointer, so that's fine. It sets the uniform okay, we know that because we were just debugging that function. See if the value is correct. Oh my god, so many conversions. The value is, oh, that's not a color. Well, so colors can't have values above 1. They're like from 0 to 1 if they're floats. If they're integers, from 0 to 255. But that's fine, it'll just show up white. We can fix that later. But the uniform is valid. Yes. So that's fine. Let's take a look at the scaling matrix. Ooh, it's pretty small. It's very small. So maybe it was using a different scale for the seaweed than I'm using. And let's see. I don't know what scale I'm using. How big is my... Oh, I do remember. I do remember. My scale is that... So my little guy has a height of 2. So if anything is too small, like if it's 0.001 or something, we won't see it. So that might be a problem. So let's... Like 0.03, that's pretty small as far as thickness goes. So let's bump that up a little bit and make, you know, I'm basically going to multiply everything by 10. Okay, thickness went up, link length went up. That should do it actually. I'm not sure that that will make these things appear, but But let's see if it does anything. Gotta disable the breakpoints. Okay, yeah, still nothing showing up, which is fine. Which is fine. So let's keep stepping through. Re-enable the breakpoints. So now this scale matrix should be okay. So that's a pretty thick seaweed. It's going to be half the width of me, but at least we know that that's not the problem of why it's not showing up. So let's see. We calculate a centroid for the little ball at the end of each link. Oh, everything's too far away from the camera. Let's uncomment that. It thinks it's too far away from the camera, so it's not drawing it. That's no good. Please recompile things when I ask you to. Okay, that wasn't it. So let's keep stepping through. All right, we have some seaweed lengths. Let's take a look at this matrix that we're passing in. Yeah. Yeah, this is laid out the way it's supposed to be, I'm pretty sure. Should be no problem. It's kind of big though, oh my goodness. So this is the position of, actually, what is this scale thing? What's that all about? Scale. Oh, this is a matrix rotation. Oh my goodness. This is a matrix scaling. Oh, so this is probably wrong actually. It needs to be like this. M2 equals scale times M. And then we pass M2. Yeah. So I thought scale was a was like a floating point number, but it's a matrix. And so what we were doing is we were multiplying. What is this? This is probably a vector. We were multiplying a matrix by a vector, yeah, and then passing that as the translation. But what we really want to do is do a matrix multiplication. I think in this case it won't actually matter. Is that right? It might matter. No, it will matter. It will matter. We need to do the same thing over here. So let's make another matrix, and then M2 is scale times rotate times M, and then we'll pass in M2. All right. Disable those breakpoints so we can see what's going on. Still no seaweed. All right, well, not everything can be easy. Re-enable the breakpoints. Let's take a look at that matrix we generated. Oh, of course, it didn't actually recompile it. Okay. Still nothing though. So let's take a look at that matrix now for real this time. Print M2. All right. So we have a box that is about, it's 45% the size of our regular box, and it's at this location, -11. Y is 2.25. Oh my goodness. So this might be a problem. This might be a problem in that what is the definition of up in this code? Is it Y that represents up or Z that represents up? I don't remember. In the math code, it is Y. And if it's not Y in this code, then we're going to have a problem. And I don't see anywhere that clearly indicates that. So let's see. Oh, that looks like it's a Z. Yeah, it's Z. Okay, so this code assumes that Z is up. Wonderful. That means that all of our seaweed is going to be sideways. Let's see. I don't see any seaweed under the level. Wouldn't really make sense. All right, well, we'll cross that bridge when we get to it. First, I'd like to get something rendering. So anyway, let's see. This matrix looks correct. So let's render the box. Come on, come on. All right. Let's see what these matrices look like. Transformation matrix is 0? Is identity? I thought we filled the transformation matrix with a bunch of stuff. It shouldn't be identity, I don't think. Oh, that's why. Yeah, it's our uniform that we set is being overridden by this code. So we need to do this another way, and that's fine. There's some code somewhere in here that sets the transformation, and we just find it and use it, and here it is. Set transform. Well, this multiplies the current transform by a new one. We just want to set the transform. Reset. Okay, load transform. This is it. Load transform M2. Actually, let me do it this way. I keep forgetting I have this nice feature in Sublime that lets me type in 2 places at once. It's really clever. Okay. Good. I don't know if that will do anything, but let's see. Yeah, still no seaweed. What on earth? Let me just do this, just so we know we can get something rendering. I'm gonna render a box at what should be the origin, I think. A red box. One, 0, 0, 1. Because I'm starting to get kind of suspicious that we haven't gotten anything rendering. So let's just render a simple red box. Get that showing up. Yeah, see? No red box. What's going on, guys? What is going on? Let's do it this way. Maybe this code knows something I don't. Ugh. Oh. See, this is when the multiple the multiple editing backfires on you. All right, what did it do? Put those back. Get renders, not okay. There we go, a red box. All right. At least now we know we can render a red box. All right. So then, why aren't the seaweeds rendering? Is the next question. I don't see any seaweeds. What is that? So this box is getting rendered with all of the same settings as the box that's supposed to represent the seaweed. Except for this load transform. Well, and the color. Yeah, maybe the color matters. I doubt it, but oh wow, it was the color. All right. That doesn't look like seaweed at all, does it? And it disappears when you get too close. Well, at least we got something rendering. So let's see, let's fix this color. It's probably this ×2 that did it. I don't know why that's there. Ooh, we're back to nothing. You know what I'm gonna do? You know what I'm just gonna do? I am going to so this uniform has some values that it wants this vector to be. I'm just going to copy and paste them. Here they are right here. And now they're exactly where they need to be. And now this call is in the same format as that call. I don't know what was going on there, but you know, I don't really want to spend time trying to figure that out. This is already exciting enough as it is. Oh, I forgot to. That's it. It was the 0. I'll bet you that's it. I know for a fact that's it. Okay. So the alpha channel was set to 0. And so it was just discarding all the pixels. Yeah. There they are. Some really weird looking seaweeds that are having some strange problems. I honestly thought this was going to be yeah. You probably typed that. You probably typed that alpha suggestion like before you saw me do that, like before I realized it from your end, but because of the stream delay. Okay, well. So this looks like it's more, oh yeah, so this is what it's doing. It's if you're close but you're looking away from the seaweed, then don't draw it. And there must be something going wrong with that. Who knows what it is though? Okay. Yeah. Yeah. It's not the color of seaweed. And it's all on a weird line. Okay. Yeah. So step one to try and get at why this is being weird is that I'm going to turn down the number of links to 2. And let's get rid of all but one. Let's keep this one. Of the seaweed positions. I really wish it would actually build it when I press the build button. I thought I just got rid of most of them. Why is it still showing so many? This freaking outness when I'm near the center here, I will bet is caused by the physics simulation thinks that I'm pushing the seaweeds when I get really close to the seaweeds. So it does that. Looks kind of funny actually. A mystery. So this is where I initialize the seaweeds. Ah, that's why. It's seeing a bunch of junk in there. Okay, we'll put that to 1. For now. So there should be exactly 1 seaweed around here somewhere. Yeah, it's down there. So let's move that up. +8, +5. All right. Good. So it's drawing 2 boxes. Something doesn't seem right to me, but figure that out in a bit. It's drawing 2 boxes. Let's not worry about the little bulbs at the end of each link right now. We're just gonna worry about getting the links themselves looking right. Where'd it go? Oh, the links aren't rendering at all. That's weird. All right, that's a very long link, but that's okay. Let's print out this list of seaweed and see what we got. Seaweed, the first one. Oh, there's only 1. The position of the first link and this is tough to read, 850, 850, 850, 850. All right, well, that's pretty clear what's going on. Everything says 850, which means that why are there two positions here? So you'd think that this would just say Seaweed position and then the number of links. But I have like 2 positions per link. Oh, I think I know why I'm doing that. Yeah, I do know why I'm doing that. No, maybe not. Huh. Well, so that's a little bit of a mystery. I don't remember why I did it that way. Let's look at the simulation function. Maybe that will give us a clue as to why it was done that way. Oh, of course. The K is the number of seaweeds. Wait, really? No, that's not right. Okay, this is the, oh, of course that's why I did that way. Okay, so when I do my simulation, am I doing a Verlet simulation? I think I am. Current position, last position. Yeah, okay. Okay, so it all makes sense. Well, I'm gonna cover Verlet simulation, Verlet integration later in the series, but what it's doing, so the upshot is what it's doing is it's calculating the velocity by taking the difference between the current position and the last position. So in this case, like, well, so if the current position and last position are the same, then of course that means there's, velocity is 0. So that's why it needs 2 copies of each. Okay, so that answers that question. So where was I? Right. So then this will be 1 copy and this will be the other copy. Which one of those copies is it rendering right now? I'm not sure. But still we see that the base of this link is in the same spot as the top of the link. So let's do this. Let's go to the initialization code and see what it's doing. All right. It's setting the initial position to, see, that's something that we need to change. It needs to be, the middle component is 0. And then same over here, the middle component is up. All right. So now, all right, now we actually have a different value here. This is 805 and this is 83.55. So now let's go to the simulate seaweed function. Well, first, before we do that, let's just visually inspect the simulate function, see if we can find all the places where we need to change it. so that y is up. And not going to worry about this for now. This is a this cycloid is a function that simulates sea waves going back and forth, so that the seaweed goes like, you know, kind of left and right. So we have a buoyancy simulation that needs to point up. We have the surge. The surge needs to point laterally. Okay. That looks like that's it to me. Yeah. So we'll compile that. Now let's see what the simulate seaweed function is doing. It's just a bunch of setup stuff. It's pretty boring. So current position and last position. Current position is the same as last position. That's going to be true because it's the start of the simulation. The seaweed's not moving. But the lower link position should be different. Yeah, so that's a little different. That's fine. That is the depth of the water. Yeah. I don't remember why I needed to know the depth of the water, but oh yeah, to calculate how much the force would be on the, how much, you know, the water pushes the seaweed around. Okay, we do some stuff. We calculate how much it pushes stuff around. We figure out whether player is close. That is a value I would like to know. Away from player. Oh, of course, the player is at the origin because the game is just starting. So, so that looks the same as the, you know, the position of the seaweed. Okay. So that's too far away to try to avoid the player. And then, oh, this is actually something we don't need. So this is the force that blue thing in the middle of the video exerts on the seaweed. But yeah, but we don't need it. Blue force can be 0. So I think we just delete all of this. Everything that says blue can go. Good, I didn't break anything. So where were we? So we calculate the force. What is the force? The force on the seaweed is huge. Oh my goodness, what? Why is it that big? That looks fine. That looks fine. That looks fine. That does not look fine. So this avoid player thing, this is probably the problem. Oh yeah, see, it doesn't get initialized. There must be some subtle difference between my math library and the original math library that this lived in. Okay. So that's one problem fixed. Uninitialized variable. What year is it? And we're still running into uninitialized variable problems. So now the force should be something reasonable, and it is. So then we calculate the acceleration from the force, and it's also reasonable. So now we calculate a new position, and that looks okay to me. Not sure why this is happening. Oh, you know what? That needs to get updated to .y because that is up. Yeah. So that's just saying what is that saying? Thinkness. I'm not sure why that line there is there. I think it might be a mistake. I'm going to leave it there for now. But it seems like it is a mistake. Or maybe, yeah. Yeah, I'm pretty sure that's a mistake. I'm just going to comment that out for now. No, I'll leave it in there just in case. So the new height of, like, after you do the simulation step, the new height of the seaweed should never be less than the thickness of the seaweed. That doesn't really make much sense to me, and it seems like it'd be a no-op because everything is always going to be above the floor. So, like, the height of the thickness of the seaweed, of course, is going to be, like, everything's going to be above that. Seaweed is not very thick. I don't know why that line is there at all. Yeah, I'll just erase it. Okay, moving on. So we've created, so this is an offset of where the new position should be. Oh, and finally we get to our fixed point iteration. So the section of seaweed, the new section length has been calculated after all these forces have been applied. And so now we do the fixed point iteration. We say what's the new length. Print R. It is 0.99992. Okay, it didn't really move that much, but after the fixed point iteration, oh, sorry, that's not the new length. That's how much to scale it to make it be the length that we want. And so we do the fixed point iteration, and we see that now it is. Yeah, now it's moved a little bit. So it's gone down, it's like its height has dropped a little bit, and it's moved laterally some. So pretty boring. All right. Good. And then yeah. So this is where it switches the two lists, because we just use one list to calculate the other list, and now this list is current, and now we swap which one is considered current. So now this is the current one, and we'll use this one to generate that one. We'll just ping pong back and forth between these two lists. That's pretty cool. Huh. But I don't see anything. Yeah, I still don't see anything. That's sad. Okay, well, let's go back to the render function is what we were looking at before. Actually, you know what? Let's take one more look at the simulation function to make sure that in all that time that we just spent simulating, nothing weird happened. So yeah, no, this looks reasonable. We have a single link, and its length is about what it should be. It looks like it may have drifted some. So no, that looks okay to me. That looks okay. But they're no longer like identical like they were before. So we've made some progress. Render Seaweed. So where were we? We're going to render a link of Seaweed. We're going to skip to the end to see what the matrix is that we're passing in to OpenGL. And here it is. That's some weird stuff right there. These values should always be 0. Oh wait, is this matrix sideways? What is going on? Why is this? So as you know, if this is your regular matrix like you normally get, you have one column that represents your forward, like your forward direction, a left or right direction, this would be the up direction, a left or right direction, and then a translation. And the forward vector has 1 as the W, and that's not right. It should be 0. Yeah, it got set to 0 right here. But you know what? Oh, give me a break. Yeah, it wasn't set. Okay. So this is because of that set forward vector function that I wrote. So let's go in there and complete it. I thought it wouldn't be necessary to set the fourth one, and I guess I was wrong. So let's make sure that everything is hunky-dory. What am I doing? Yeah, double checking my work. Oh! Good thing I did. When you're writing something from scratch, you don't really run into these problems because you have like the full picture in your head. But when you're redoing code, you don't have that full picture, and so things are kind of more confused. That's my excuse. Scale matrix looks okay. Yeah, there you go. That looks a lot better now. So I guess I kind of deserve a lot of these problems that I'm running into, since my original work wasn't terribly thorough in, you know, engineering quality. Okay, yeah, this definitely looks like a good matrix. Our width is 0.24 here and 0.169 here, which is weird that they're not the same, but I'm willing to accept that. And then our height is 2.4. That looks more reasonable. And then we have a translation of a little bit. That looks like it might be half the height of the, you know, you have a box and then you move it up half the height so that it goes from this point to that point. So that looks good to me. Let's see if we fixed anything. Yeah! Okay. That kind of looks like it could be a seaweed now. Not really. Well, it looks more coherent than it was before anyway. Yeah, so I think the first problem is that it's wide instead of tall. That should be pretty straightforward to fix. And I think I know exactly why that problem is happening. This is the issue with the up direction being different. Oh, and here it is. That's up right there. And that means this one will be left. So that will probably help. Yeah, okay, that did something. That didn't really do what I expected it to do. What on earth? Well, I've seen weirder things. Alright. At least it's facing the right way now. So now, let's see. Now we're going to have to examine this math here more closely. So the next link. Okay, so it does a little math to figure out what the direction to the next link is. Okay, bud. Hey. Hey. Calm down. Calm down. They're just walking by. Calm down. Okay. He's defending the house. So we're going to cross product that with the up direction. That will get us something that is pointing to the left. We'll cross product that with itself to get a local up. So this would be good if I could draw a picture. So we have cross product of up and where the link is pointing. That gets us something that points to the side. So we're going to cross product that thing that points to the side with the direction to the original direction to the link to get us what the link considers as up. So it's like adjusting the up vector for the direction that the link is pointing. Yeah, sorry. Sorry about the loud dog. I bring him to work a lot, and he sometimes barks at a coworker, and that can be embarrassing. Okay. Let's look at this in the debugger. That's what I want to do. Actually, you know what I'm going to do for now? I'm going to go back to the bulbs. Because the bulbs are a little bit less tricky as far as like matrix math is concerned. Because the bulbs are just a box rendered at a location. So I think if we can get the bulbs right, then it might be easier to come back and do the other stuff. So I think, hey, it's fine. Relax, bro. Don't need this breakpoint anymore. All right. Well, actually, let's just see what it looks like. Okay, yeah. So we have one bulb at the base and one bulb a little bit higher. That's about right. The bulbs are kind of big. So let's maybe make them a little smaller. Yeah. But I think that's about what they should look like at this point. Oh, that's probably too small. Are they moving around is one of my questions. It doesn't... Oh, yeah, it is moving a little bit. I don't know if you can see it on the stream. It's moving only very slightly, which means it's being simulated properly. So we're making some small amount of progress. Okay, yeah. When there are many more links, it will be... In fact, let's add some links. Let's have a little fun now. Let's pull out all the stops. Oh my god. Oh wait, how many links were there to begin with? I don't even remember. How many links were there? Really? Oh, this file isn't versioned. Damn it. Let's look in the original file. $16 links. All right, we'll pump it back up to 16. Yeah, a nice stalk of seaweed. Let's make it a color that's more easily seeable. I don't know why it's this weird yellow color. That doesn't look very seaweedish. It should be more green. Here's the color, red, green, blue. Let's change red and green. I didn't do that right. That doesn't look green either. Still looks kind of yellowish. But you can actually see the stalk now. Or maybe you can't on... Okay, let's make this a darker color. Because it's like... It's against that blue, and so you can't really see it very well. Let's make it black. Yeah. Black seaweed. Now we can actually see it. All right. And make these bulbs a little bigger too. Yeah. It's really pretty, Seaweed. All right, let's see. Let's take a little closer look at it. It does kind of look like it's moving. Actually, maybe I can get it to... No. It's supposed to respond to the player, but this one doesn't seem to be. Weird. But you can see it moving very slightly up there. Maybe you can't on the stream. Let's get it to move. Let's kick up the surge by a factor of 10 and turn down the drag by a factor of 10. This will probably make it freak out. That didn't do anything. What? It's like waving around slightly more. You probably can't even see it on the stream. Yeah. Yeah, that's not very exciting at all. Okay. What do I have to do to make it more... Well, I should just affix this player avoiding part of it. Okay, let's do that. I should probably go stand next to it first. Standing next to... Oh, it's got a little kink in it now. You can probably see that. Oh yeah, it's kind of waving. Yeah, you can see that. It's waving. All right. Just like Seaweed does. Does Seaweed do that? I have no idea if Seaweed actually does that. Okay, so now we're standing next to it. Let's hop in there, see what we got. That's fine, that's fine. So we're gonna skip to the section where it detects where the player is, avoid player. So, what is the distance to the player? I'm gonna step into this player get global origin function to make sure that's returning the right thing. And yeah, I think that's correct. That's more or less, yeah, all right. All right, so then the distance to the player is print away from player. Ah, yeah, because, okay, so here's one problem, I think, is that the player is thought of as a, as the origin being at the player's feet, and so that means he's kind of far from, like, his origin is not at the center. His origin needs to be at the center. So, like, if the origin is at the feet and all the links are up there, then it's not gonna, you know, it's not gonna do anything. All the links up there are gonna be too far away. So let's just, get global origin. Let's see if there's some kind of function I can use instead that instead of giving the origin, it gets the center. Does that exist? Oh, maybe this. Get global AABB, and then I can get the center. Get the center. Okay, so that's what I'll do. Get global AABB, and then get center. So I'll get the center. Then we'll have some distance we are away from it. Okay, so we use the distance. I see. I see. This is what we need to modify. Yeah, that's tiny. Let's kick that up to 5. So this is the distance that the player will affect, the distance at which the player will affect the seaweed. And we're going to kick that up a factor of 10 like we've been kicking everything else up a factor of 10. Oh yeah, I did mean that. You could figure that out. Like, if the compiler can tell me that I meant to use a period instead of a pointer, it should just accept the period instead of the pointer. Like, it knows what I meant. All right. There we go. Well, it's not responding to me as fast as I would like. But you see it did make a kink right here. And now if we stand back and look at the whole thing, yeah, it's doing something. It's waving. That's exciting. Let's see if we can't get it to wave some more. So I already kicked up the surge force, and I turned down the drag. Do I want to just do that some more? Maybe reduce the buoyancy a little bit. Yeah. This buoyancy is such a drag. Okay. So the surge will kick up a little more. The buoyancy we already turned down. Because the buoyancy just makes the whole thing want to stay up. And we'd like to flop it around a little bit. So if we turn down the buoyancy, I think that will help. What did we just do? Did we turn down the drag? Oh, let's turn down the drag. Turn down the drag. All right. Oh yeah. You can definitely see it going a little bit more faster. So let's see what happens if I do this. Come on. Oh wow, it was so easy to do it last time. It doesn't want to do it anymore. That's weird. Oh, there it goes. Oh. Oh yes. I remember what that line of code was for that we deleted. Yes. Yes, that line of code was important. Yes, it prevents things from going through the floor. Now, as entertaining as this is, that line of code should probably still be there. So let's go find it again and add it back in. Closing some things that don't belong. There it is. So, yeah, we're keeping things above the floor. Yes, that should do. Also, this is the simulation function. Thanks, Jan. It took long enough to actually get it working again. Jeez. I thought it would take like half that long, at least. God, what was I gonna do? here. What was I gonna do? Why did I come over here? Oh, I don't even remember. I hate it when that happens. What was I gonna look at in this simulate seaweed function? Oh well. If I can't remember, it must not have been very important. Oh, I remember. I'm gonna, let's see here. So something's weird with the distance avoiding function. So with the player avoiding part of this. So I wanted to take another look at that. We have the distance from the player. We get the length. If that is, so if we're inside that distance, then we push away from the player in a normalized direction. Yeah, so I think I'm just gonna kick that up a little bit more. Kick up that distance. It doesn't really seem to be responding. And we'll go to 10. Once it kicks in, it seems like it's doing fine. Like, it affects it a lot if I can never actually get it in the right place. So, I mean, at 400, that's a big number. So, all right. Let's try it again. Oh, wow. That was fast. Yeah, see? Now I'm really pushing it around. Yeah. Maybe I should turn the buoyancy back up. It apparently doesn't weigh anything anymore. Kind of looks like a snake. Ooh. Yeah, I think I need to turn the buoyancy back up. Buoyancy. Back up. The other thing I did is see, instead of just saying 1 here, instead of just saying 1 here in the buoyancy vector, I say n, which means that the higher up you are in the chain of seaweeds, the more buoyancy force you get. Because 1 is the lowest link. And, you know, like the highest link is whatever it was, 16. And I think that helped to combat this kind of weird screwiness that it did on the ground. Yeah, it seems to like fall like this a lot. I was able to combat that in the video, in the actual video, but it kind of looks cool here since it helps demonstrate the functionality of the whole thing. Yeah, pretty neat. All right. And then this is the perk of being a game programmer, is you just get to like screw with your simulation and kind of poke at it and see what it does. Maybe I should have it respond to these explosions. Oh, I forgot to turn off that block. Ooh, this one. So yeah, I could have it respond to these explosions. And that might be a fun exercise, but I've already been at this for 2 hours, and I just want to record the code section and get to the next video. So let's just leave it at there for now. This could, of course, be up on the interwebs for anybody to mess with it. Let's uncomment the section that renders the links and see what it, oh yeah, you know what, I really don't want to fix that. I really don't want to fix this. Okay, yeah. So here's what I'm gonna do instead of fixing this code. I think I have, so what this code does is it, thank you guys, is it creates a matrix that transforms the box, like the standard box, like this -1 to one box into a long straight thing. And like we could figure out that math, but I really just want to move on to the next thing. So I think what I'm going to do instead is, if there's like a render line function, there should be render lines. Yeah, that should work. So I'll just render a line from the old Seaweed position, or from the new one. This is about to be the new one. Vertex. From the old one to the new one, and comment out the render box and make sure it actually compiles. And oh yeah, so now there's a bunch of stuff that's not being used. That's fine. Just make it go away. Oh yeah, don't need that either. All right. So we're just gonna render a nice, simple connecting line. And oh, yeah, why did it do that? That's weird. That's the line I want, but obviously it's offset a little bit. So let's go see why it's offset. And oh, what am I doing? This is simulate Seaweed. Yes, and let's make render Seaweed. Let's go to that. Oh, 283. No, it's not. Thread until 283. 283 is the line I want. What? That's weird. Why does it think that? It's not letting me run to a line in the source code for some reason. You know what I'll do? There. Okay. So, oh, of course. Of course, of course, of course. So what was happening is that the transform that was set up here was still active down there. So that's actually an easy fix. I think reset transform is a function. I just saw it. We looked at it like half an hour ago. No, it's not reset transform. It's reset transformations. Okay. Transformations. Sometimes when I'm coding, I'll make a bunch of different variations of spelling of the same function, and then they all just call each other, so they all do the same thing. So I don't have to remember like minor differences like that. Is it transform or transformation? Who cares? All right. Oh, weird. It's still not in place. And why not? Okay, is it this one that's drawing wrong or that one? And I think it's the bulbs that are drawing wrong, honestly. Hold on. This is knowable. Oh my god, it's the bulbs that are drawing wrong. So this is why it appeared that the bulbs were that like, okay, this is why this is why it looked like the player physics interaction radius was too small. It's because the bulbs are drawing in the wrong place. The physics interaction radius is fine. Like, it's, you know, I'm way over here and it's getting pushed away. So that's fine. So I need to go back and turn that down again. And the bulbs are definitely drawing in the wrong place. Seaweed player distance? I think that's what it was. We'll put that there. And then fix where the bulbs are drawing. How do I do that? I think I just want to get rid of the scaling. I don't need the scaling, do I? I don't think I do. Oh, I already did. I got rid of scaling. Let's see if that does it. Yeah, so now the bulbs are really big. Yeah, this feels a lot tighter. Yeah, okay. So that's good. And we're gonna get rid of this. And, oops. And I think we can even turn down this distance a little more. Okay, and then we can render these bulbs a little bit smaller since we don't have that scaling in there anymore. What is the scaling? Seaweed thickness, what is that? 0.3, okay. Let's just do this then. It's already at 0.3. All right. What's 0.3 times 0.3? It's 0.09. Just make it 0.1. Okay. I think that should do it. And now I'm going to come up here, and we are going to really go crazy, go nuts. Or what is it that Casey says? Banana cakes. We are going to go banana cakes, and we are going to turn all of the seaweeds on. We finally get the payoff here. We get to see all of the seaweeds at the same time, and we get to run through a forest of seaweeds. Oh, they're all in one place. That's boring. Well, let's run through a forest of seaweeds. Wow. That was anticlimactic. It's not responding to me anymore. I must have turned this physics distance down too much. Let's put it back up to 10. It's not going to kill us. I want to run through a forest of seaweed, damn it. We've worked hard, man. We deserve that forest of seaweed. Yeah! It's like a big onion. Whee! Alright. Fun with physics, people. That runs pretty fast, too, huh? Yeah, let's turn that back down a little bit to 4, something like that. Full on banana cakes. You guys aren't moving enough. Success. Okay, I think we're ready for the code portion of this video. to record it finally after 2.5 hours of code. So totally worth it though. Totally worth it. So this is doing 29 seaweeds, I think, and my frame rate is fine. And the reason it can do, I mean, I think it could do even more, honestly. I wonder. Well, it would be pretty hard for me to kick it up because I had to manually place all of them, and I don't want to write a function that automatically places them. Or else I would totally kick it up to 100 and see what my frame rate does then. But yeah, the reason why it simulates so fast is because I used a few tricks. And we'll go over them real quick before we do the code section. So one was the trick, I think I already mentioned it, where you use two copies of the positions of the thing. One that's like the current position, one's the previous position, and you use previous and current to calculate the next position, and you store it where the previous position was. So this has a lot of good properties. For one, like, you're not... Wait, no, I shouldn't say that. That wouldn't be true. Anyway, it's Verlet integration. I mentioned it before, and it's like the math is a little bit faster. Here's the Verlet calculation right here, and it calculates velocity. And then you use the velocity to calculate the new position. So that ends up being a little faster. The fixed point iteration we did avoids having to do a square root. So that makes it a little bit faster. And the fact that I just stored this as two arrays, like you saw how I did it. So seaweed is... These are all the seaweeds, and then there are two arrays of vectors, and so when I do the physics simulation, I do it lockstep with each array. And so I'm modifying contiguous memory, and I think Casey has talked about contiguous memory before, and I have also in my videos, and so like if this were 16 seaweed classes, then all of the vectors that represent the positions would be scattered all over the place. It wouldn't be as fast because of memory caching problems. So good. That was fun. Let's do the actual video now. So this is the functional part. That's already paused. This is the functional part. Let's see, we have float. So this is the code that I actually want to write on camera. And let's see, we'll go to a single window layout. Usually I do a step of organizing the code a little bit before I actually do the recording, so that it is a little more clear what I'm doing. For example, this link length squared, like what is that? We have to map that to the actual like fixed point formula that we did before. So let's bring up come on, Camtasia, where's my mouse? And take a look at the video we recorded last time called Untitled and see what formula we used. Here it is. So L. So I think I'm just going to call this thing L. Let's see. Link length squared. Yeah, see? So I'm going to make float L equals G seaweed link length. And then I can say L times L and L times L. Not very optimized, but that's fine. Now this other variable s, this thing is called section. So I don't really think I need to rename that because it starts with an s. I feel like that's pretty clear already how that works. Yeah, and then we can 2l squared, or yeah. And we scale. So that looks good. That looks good. So this is the code that we're going to write. Taking a screenshot. Load up the screenshot. Move it to my second window so that I can use it as reference because I cheat. I'm going to call this new position instead of normalized position. I'm sure the word normalized made sense to me when I was writing it, but new position is more clear. And yeah, at this point, I think we're ready to start. Just close some of this stuff. Clear up the desktop. This is the thing that I just put over there, so I don't want to delete it. Oh, I can't hide it? Whatever. All right. So Camtasia, start recording. And for the code section, we have to record the entire screen. And does the microphone work? Microphone check. Hello? It says it's using the Yeti, so that's fine. Is it? Yeah, that's totally using the Yeti. All right. Let's do a run through. Welcome to the code section of the video. Here we are. Wow, I haven't thought about what I'm going to say at all. Okay, I should probably think about that. So dry run. Well, it's really a wet run because I'm recording. But we'll just throw this one out. So we have our formula. What was the formula? What was the formula? Put this over here too. Great. I cheat. All right. So we have our formula for fixed point iteration that we can use to simulate this seaweed, and here's the essential part of the code. I have oh, I already have something called new position. Oh, that's no good. That's why I called it normalized. Ah, okay, I can explain that. I can explain that. So I've done my physics simulation on each link, and at the end of each simulation, I have a new position for the end of that link. But now I need to normalize it and make sure that it is the length that I want it to be. And I'm going to use fixed point iteration to do that normalization. The first step is to create what's the word? Coefficient? Well, I guess it's to calculate what's in the brackets. And so we're going to do that. There's 2 times L squared over length of S squared, which we discussed. We can write as a dot product of the section length with itself. And then I'm going to add in L squared again. And now that we have this scalar, we're going to multiply the, Let's do it this way. Vec3, new section. This is what we want. Section times R. And then I'll just say lower link position plus section. And that will be part of the code that I don't write. Okay. Okay, I think that's good. So let's start this recording over. And do it maybe for realsies this time. So here we are in the code, and we have our formula that we want to use to correct the length of a section of Seaweed. We've done a bunch of physics stuff up here, physics stuff that involves buoyancy and forces and all this stuff. And now we have the new position of the end of our link of Seaweed. And we need to correct that to make sure that the section of Seaweed stays the same length that we want it to stay. And that length here is going to be L. Okay? So we're going to apply our formula. 2 times L times L divided by, and now how do we get this length of x squared? Just like we mentioned, we can use the dot product of the vector with itself and then add to that L squared, which is L times L. And actually, so that will get us a floating point number. So that gets us just what's in the brackets, okay? So if we want to get a new section that, so let's see, new section is going to be the result of this expression, and we're going to get it just by taking the old section length and multiplying it by the scalar r, and then we'll have the new section length. And then we go on to figure out what the position of that is in the world, and then update our list of Seaweed lengths. So let's build that. Seriously, let's build it. Okay. And then we'll go over here to the debugger and run it. And here they are. These are the Seaweeds, which are becoming steadily longer. Why are they doing that? Why are they getting longer? This is bad. I messed up. I screwed up somewhere. I confess. What did I do? What did I do? What did I do, guys? Oh my goodness. All right. That's hilarious. Okay. Good. So the program's not completely messed up, I just typed something wrong. So let's start again. Vec3, new section. All right. Oh, I didn't use new section? Did I use old section? Oh, okay, well. Let's try it again. Maybe this time I'll actually use new section. No guarantees. All right, here we are. This is the code that physically simulates the Seaweed. And you can see I do a lot of physics stuff up here. And we have some buoyancy and some forces and some accelerations and stuff. And then we generate a new position that our seaweed is going to be in. But there's no guarantee that that seaweed section, the section of seaweed, is the length that we want it to be. So we are going to do a fixed point iteration now to reset the length. So here's the formula. First, let's do the part that's inside the square brackets. So that's 2 times L squared. And then we're going to divide by the... Oh my god. Oh my god. I guess I just got a phone call. All right. Should probably close that tab. Yeah, thanks, buddy. Well, whatever. Hopefully no one calls me again. Okay. Okay. Third time's a charm. All right. So here we are in the section of the code that physically simulates the seaweed. And you can see up here we're doing a bunch of physics stuff involving buoyancy and forces and things. And we use them to generate a new position for that link in the seaweed. But there's no guarantee that after all these weird physics stuff that we've done, that the new position is exactly the length, the distance from the next length of seaweed that we want it to be. Like it could make the seaweed go long, become low. Oh my god. My damn friend had to call me in the middle of what was going to be a great take, and then every take after that just gets ruined. Ruined. It'll never be as good as that take ever again. All right. Take 4. Here we are in the function that simulates the length of the seaweed. And I'm sorry, simulates all of the properties of the everything about the new seaweed. The seaweed is amazing. I'm gonna get some water. I'll be right back. Let me get some water. That's what I need to not screw up. I just need some water. There have been takes for these videos where I've had to do it like 10 or 15 times before I'm finally really happy with the result. But that's when I was first starting the videos, and like, you know, I've gotten a little better at it. Okay, we've had some water, we've had some practice. Let's do a non-crappy take. So here we are in the section of the code that simulates the seaweed, and you can see that we do some things with buoyancy and some forces and acceleration, and then we eventually calculate a new position for the seaweed, for a single length of the seaweed, a single section of the seaweed. But after we did all these physics calculations, there's no guarantee that the length of our new section of seaweed with the new position is the length that we want it to be, this seaweed link length. So we're going to do a fixed point iteration, and it's going to be exactly the formula that it's on the screen now that we just talked about. So that is, and we're just going to do the parts in square brackets right now. So 2L squared over, and then like we discussed, we can get the length of S squared squared, S is the second section, by doing a dot product with itself. And then finally plus L squared. So that gets us the part in the square brackets, which is a floating point number, which is a scalar value. And in order to get the new section length, we have to take the old section length and multiply by that scalar number. And then we can continue with the rest of the calculations. We have the new section length, so we add it to the lower link position to get the new normalized position, and then we update that. And so this should be everything that we have to do. So let's build it and thumb over to the debugger and run it. And here we are. Our forest of seaweed, and it even interacts with you. Pretty cool. So that is our first in-practice use that we have seen of root finding functions. Well, I suppose that fixed points aren't technically root finding, but you can, since we discussed, you can convert any problem in fixed point to a root finding function. It's pretty much the same thing. So next week, or right now if you're watching the stream, we are going to go over the last and most powerful root finding technique, which is Newton-Raphson iteration. Super exciting. See you then. All I needed was the water. That's all I needed. All right. So we'll put that there. And I think I'll do the actual editing of the video another time. I'll do that off stream because it's boring. But I'm going to call a wrap on that one. And that is saved. So now let's talk about Newton iteration. And for that, I'm going to have to get out the tablet. So give me a moment to set up the tablet. At least my friend called me at the beginning of a take and not like when I was almost done. It would have been a shame if he'd called at the very end of a really good take or something like that. All right. Okay, that works. And let's do some mischief. Oh. I'm gonna have to do some folder organization. Might be a little boring. Newton. Yep, Newton. Everything else can go. Oh, you missed a lot of trying to figure out, trying to get the Seaweed to work because I had to port the code over from that Blue Ocean project. So That was just a lot of debugging. All right. You actually probably got here at the least boring part of it. All right. So, yep, 2 hours of debugging is basically what it was. Let's see. Let's go back to Burden and Fair's numerical analysis, and we'll find Newton iteration. Newton's method. Oh, that's a link. Good. Perfect. And here's a good picture. Great. Newton's method can be somewhat tricky to draw a picture of because everything kind of gets clustered. So I wanted to find a good picture. And this is a pretty good picture. Let's redraw that picture. So here's the idea. You have a function. You're trying to find what the x value at this point is. So if you can get close, let's say this point, okay? The x value at this point is incorrect. But if you know the derivative of this function, I'm going to draw the derivative at this point, okay? The derivative, remember, is the slope. The derivative is the same thing as the slope. So I drew the tangent line of the function at the point x. Okay. Now that tangent line itself has an intersection with the x-axis. And notice that it is kind of close to what we want. So, zoom and enhance. Ooh, that worked. Zoom and enhance. So here's the new, so this was our initial estimate. We'll call it x0. So now we have a new estimate of what our intersection is. Call it x1. So now we're going to do this process again. We evaluate, let's do it in another color. We evaluate the function at x1 and then find the slope, find the derivative at that point. Okay. Here it is. That's a pretty crappy derivative. All right. Now that derivative line has an intersection with the x-axis. Here it is. So that's going to be our new estimate. So zoom and enhance. No rotate, just zoom and enhance. Zoom and enhance. So you can see we're like 2 iterations of Newton iteration, and we're already pretty accurate. Like, if this was the original line, and I drew it not straight intentionally, let's see. Let's make this the original line. And now this is our, like, we're really damn close there. So let's do it again. Like, at this point, Newton would have, like, Newton is a physics engine. His brain is just a gigantic physics engine. All physics comes from Newton. It's not really true. Okay, so like you can see how close we are to this, to the actual result after only 2 iterations. Newton's method is really cool, and it converges fast. It converges super fast. And that is specifically because most functions, like a continuous function, here's a continuous function, okay? Locally, at any given point, pick a point. That point right there, if you zoom in enough, that function, like, you can kind of see it with this blue function. It almost looks straight. The more you zoom in, the straighter it gets. So, so that's why Newton's method tends to work so great, because it basically zooms in. And then the more it zooms in, the more accurate it gets. But what are the limitations of using Newton's method? So let's talk about that. And now that I've zoomed in, can I unzoom? Yes, no. Oh, I didn't want to erase everything. Give me my stuff back. Oh, everything's gone. Oh, awesome. You know what I'm just gonna do? Don't save. Open it again. Huh. All right. Thank you. So. All right. So that's Newton iteration. Newton's method. And I'm going to write out the steps right here. Let's see, you have a function f of x. Okay. F of x has to be continuously differentiable. This is some math notation. That means it's continually differentiable. That's what it means. It means that you can take the derivative of it. I hope everybody in the stream is familiar with what a derivative is. I did cover it in one of my videos, so hopefully you are. But the upshot, of course, is that the derivative is the slope of the function at a given point. So the other thing, oh, no, let's continue writing. So then, since it's continually differentiable, then you have f prime of x at any given point. So let's draw our graph. Okay, here's our function. Here, say this is x naught, and then okay, then we have your x right there, x naught. So the derivative of x naught is important, and the value of f at f naught is important, and we're going to figure out what the formula is for this line. Derivatives are your life. Okay, sounds like a good life, gangster. We're going to figure out the formula for this line by using this nice formula right here. The point slope notation for a line. Probably covered in like high school algebra or something like that. Super useful formula. And what we're doing is we're solving for when x equals 0. Right? No, I'm sorry. What am I talking about? We're solving for when y equals 0. So this is the formula for this line right here. Given x naught, which is that, and y naught, which is f evaluated at x naught. Okay, so that's the point right there. X naught, y naught. Good. And so x naught, y naught is there. And then m is going to be your slope. So we know how to get slopes. That's a derivative. And so then we know we want y to be equal to 0 along this line somewhere, because the x-intercept, the intercept with the x-axis is exactly where y equals 0. So this is just going to be 0. So let's rewrite this formula in a new color. X minus x naught, that stays the same, equals f prime of x naught times negative, well, instead of y naught, I'm going to say f of x naught. All right. And now we're going to solve for x. So x equals f prime. Did I do that right? Why does something look weird here? F prime of x naught. Do it this way. X naught minus f prime of x naught times f of x naught. Does that look right? I think that's right. So that will solve for the x value at that point. And then we're going to take that as a new x value and do this process again. So to generalize, if we have a sequence of x's, each one is more accurate than the last, then we get each one by following this formula. All right, I just substituted 0 for n and n plus 1 for 1. I wish I had my graphing calculator with me to see if this is good, but I think this is good. I think this is the formula. Let me double check in the book to make sure I have the right formula. And, oh, it has the derivative in the denominator. And it has a denominator. Yep, I did something wrong. I did something wrong. Oh my god. Good thing that this is a test run. Let's try it again. That is point slope formula. All right. All right. And we want when y is 0. So let's solve for x now. So we get, let's see, this is negative y naught is f of x naught equals f prime x naught times x minus x naught. So this goes under here. This is making a lot more sense now. And then we add x naught. So we get x equals x naught minus f of x naught over f prime of x naught. Good. That's correct. I'm sure of it. And yeah, let's give a shot at using Grapher. So let's just do sine of x and estimate pi like we did before. And what can we use as an estimate? We'll use 3. So let's see. That'll be 3 minus sine of 3 over the derivative of sine 3 minus sine of 3 over the derivative of sine at 3. So actually, instead of that, I'm gonna graph it. So I'm gonna write out the whole formula. Y equals m times x minus x naught plus y naught. So that will be and the derivative of sine is of course cosine. So that's cosine x, x naught is 3, times x minus 3 plus sine at 3. So I copied this equation up here. There it is. So can we zoom in? Zoom and enhance. Wow. Wow, guys. That is a really good approximation. So, .1416, 3.1426. So this is the approximation, and this is the actual curve. So you can see that they look this like if like just looking at it like this, I can't tell which curve is which. They're both so freaking straight. And that's what I was talking about. The more you zoom into a continuous curve, the straighter it gets. And that's what allows Newton's method to be so accurate. So let's do this again using this 3.1426 as a new estimate. New equation, 3.1426, 3.1426, x minus 3.1426, and I don't even want to know how crazy accurate 3.1426 the next estimate is going to be. Yeah, it's so accurate, like I can't tell the two lines apart. We're going to have to zoom in a lot more. They're still right on top of each other. Okay, I think we're starting to zoom in so much that our graph line is getting wavy. Do you guys see that? Or am I imagining that? I think that might be a trick of the eye. I'm not sure. There we go. Now they're starting to separate. It was just a trick of the eye after all. Good. So this is pretty damn accurate. Cool. Yeah. No, I thought it was floating point inaccuracy being the problem, but I think it's just because it's on this grid, and the grid is making the lines look jagged to me. But anyway, that's pretty accurate after only 2 iterations. So Newton's method, super cool. Let's talk about the drawbacks of Newton's method. When can you use Newton's method? A lot of the time. But when can you not use Newton's method? So, first of all, you have to already have a pretty good approximation of your of the function. Oh, well, we already talked about how you have to. It has to be a continuous function. They all like every function we're going to talk about for this series is continuous anyway. But you know you don't want to forget that. But you already have to have a pretty good approximation, because let's look at what happens if you use 1.7 as your initial approximation. 1.7. 1.7. Okay, so now we have a new line, and you can see it does have an intercept, but it's way over here. And so we're gonna get the wrong answer. Like, if so, let's see, what is the x-intercept here? It's actually almost exactly at the wrong. It's like almost exactly at 3 pi, which is awesome because that will prove my point even farther. So 9.4369, and I mean you can already see that, you know, when I type that in here, 9.46, 9.46, like it's giving me the wrong root. Okay, so lesson 1 is start with a good approximation. Lesson 2 is we assumed that that the function has a derivative. Not all, like, so for numerical analysis, that's cool to assume all functions have derivatives. But in practice, in video games, not all functions do have derivatives. Or at least you don't know the derivative of the function because it's some kind of weird implicit thing. So that is something that you can deal with by estimating the derivative. Okay, here's my function. If I take this point and I draw a line between them, that's a pretty good estimate of the derivative of that function at any point between those 2 points. And that's called secant method. And I'm not going to go through the math on that because I think you can pretty much imagine it given this information. So if you don't have a derivative, you can use secant method. And there are a few other methods that I think are kind of boring that are based on Newton's method, that are kind of variations on Newton's method. So super simple, actually. I mean, there's nothing more to it than that. Hopefully the Blackboard section of this video will be fairly short, actually, because I don't really feel like if I don't mess up again and write the wrong formula down, then there won't be much to explain. Which is good because that means that we can think about the code section. I feel like we just left the code section and we're already going back to the code section. It haunts us. We can't get away from the code section. The question is, what do we want to demonstrate in the code section? I mean, it'd be hard to get cooler than those seaweeds, man. The seaweeds were awesome. I used Newton's method to do the caustics in this video. The caustics. But I already did that trick. They're used a lot in physics simulations. I could use it just to calculate the like the collision of a projectile with the ground. And so the ground is a really good example of a function that you don't know its derivative. Like if the ground is a height map defined by an artist, okay, it's made up of all these like piecewise straight sections, which are maybe like, I don't know, something crazy like that, okay? And then, you know, you have your projectile going like this, and you don't exactly know at what point it's gonna intersect, and maybe you either can't be bothered to calculate a derivative, like because of the piecewiseness makes it kind of weird, and it doesn't really matter because you can just use secant method. So that just popped into my head. And I've definitely seen this method, you know, Newton's method used to do that sort of thing before. So that's cool. Yeah, I think intersection with the ground is a pretty good direction that I can go for the code section of the video. Now our ground is flat, so that's boring. And our projectiles don't really have anything crazy going on with them. So I'm really just doing this equation right here. What's the intersection of a parabola and the x-axis? Which, you know, we know how to do that pretty easily without Newton iteration. So will that be a terribly impressive demo? Maybe not. Maybe not. I could try and get these caustics working. Ugh, but we just did all this coding and I don't want to do the caustics again. I mean, I don't want to do a lot of work on the code section again. The Seaweed was pretty cool. I'm glad we did the Seaweed. We got a pretty cool result out of that. But I definitely don't want to do all that much more coding. Maybe I can go to the shader. I'm trying to give you guys your money's worth here, you know what I mean? So this is where I do the Newtons for the shader, and you can see actually that I do a few bisections first. The bisection method we talked about in the first video to get a good, and I had to do like a lot of bisections here. This is a really inefficient way of doing caustics. Don't do caustics this way. But I had to do 4 bisections in order to get an estimate that was even good enough to use Newton on. But once I have a good estimate, doing Newton actually is, look at that. So that looks exactly like the formula. Oh, that reminds me. I want to do this so I don't forget. Real quick. I just have to do this. Let me do it this way. Export. Yeah, export that so that I have it when I go to put the video together. Okay. So this so bisection method didn't really look anything like the formula, but Newton's method did look like the formula. So I feel like I can explain that, and maybe use the uneven ground example. Wait, didn't I already use the uneven ground example? Did I? Did I? Let's see. Caustics. Oh no, of course I used caustics. Yeah, for bisection. And then for fixed point I used the seaweeds. So yeah, I'll use the ground example. I like the ground example. Alright. So that means that basically means there's going to be no code section of this video, which I'm okay with because we just had a really cool code section. So opening Newton again. Clear away some of this junk. So I'm going to use the come on. The projectile as the example for this video. Finding the intersection of a projectile with the ground. But this projectile is actually a rocket. And the ground is crazy and weird and uneven. And so the rocket has aerodynamic properties like drag, and it has thrust, and it has, and it's out of control, so it's spinning. Oh my God, it's spinning. So you don't know if the rocket's gonna hit the ground, dead on, like this, or at its side, like that. It could contact here or there or there. You don't even know. So this is a perfect example of a situation where you can use root finding. And I think I just made it crazy enough that it's not like trivial parabola intersect with the ground. Okay, cool. We're gonna try recording that code section, but I'm gonna use the restroom real quick. Good dog. I was thinking, as I was peeing, that maybe I should avoid the word derivative for people who didn't take calculus and haven't watched my calculus videos yet. It should be entirely possible to go over this concept without mentioning the word derivative, because I can talk about things like the tangent of the curve at a point. I feel like that's not a big deal. Tangent line of the point, of the curve at a point. Except that I have to write f prime of f naught. F prime of x naught. And no, I can probably use the word derivative. I can say that I can use the word redundantly with the word tangent. We'll give it a shot. We'll see how it is. See how it works. So let's is that properly aligned? Here we go. Welcome to Math for Game Developers. Today we're going to do the last root finding video, and it's the most exciting because we're going to solve a crazy problem. We have a rocket. Oh my god. That rocket looks bad. I'm not putting that rocket on YouTube. Looks too much like a penis. Start over. All right. All right. Welcome back to Math for Game Developers, and today we are going to solve the problem of, we have a rocket. I cannot draw a rocket. What do rockets look like? Delete that. Not rocket jump, just rocket. Stop trying to be helpful. Welcome back, Simon. Oh yeah. Here are some rockets. I think I actually just want to use this clip art. Can I use this clip art? Is it free clip art? Yeah. I'm just going to use this clip art. It's free. Copy. Will this work? Nope. Nope. Yeah. That doesn't look like a penis. If I make it all fat like this and then put there we go. Yeah, that doesn't look like a penis. All right. This is like, it's no wonder, you know, you go into Minecraft servers and people just make penises everywhere. It's because they're so damn easy to make. Sometimes you can't even like not make one when you want to. When you don't want one. Show up everywhere. Yeah, the less roundy tip. All right. Welcome back to Math for Game Developers, and today our problem is to simulate when this rocket is going to hit this weird ground. Except that this rocket is out of control because one of its side thrusters has gone off. And so it's spinning in this direction. And it has all of this drag that's pulling it in weird ways. And oh my god, it's crazy. It's not just regular projectile motion. And this ground, it's not flat ground. It's not even regular ground. Who knows what it's like? So this is a perfect example of root finding because the trajectory of this rocket is eventually going to intersect with this line. And then so just like we talked about in the first video, we can transform this into a root finding problem. And why am I saying all this? I already said it in the first video about root finding. I'm going to watch that video again real quick. If you guys will, just the beginning of it. Because I suddenly realized, like, if I already gave all of this justification for why root finding is cool in the first video, then I really don't need to do it again. Welcome back to Math for Game Developers. Today we are going to do our first real numerical analysis algorithm. And
You have to figure out how bright it is. So physics as well, and a whole bunch of other things. So let's say you have some kind of with root finding, but this is just an example that we can use to learn what root finding is. You have to figure
here it
out
is.
what ray hits this point, and there's not always a closed form solution for that sort of problem. So this is one problem of very many that we can use root finding to solve. And now, just as a disclaimer, I don't actually recommend that you do caustics, that's what this is called, with root finding. But this is just an example that we can use to learn what root finding is and how it can be used in many different areas of video games.
What is this?
But physics as well, and a whole bunch of other things. So let's say you have some kind of function here, and you know that it has a root between A and B, okay, and B.
Yeah, it didn't really get into any
Where
other
that root is.
examples.
At what x value, if this function is h of x, at what x value does h of x equal 0? So that's what we're trying to find out.
Yeah.
H of x equals 0. In numerical, you are...
Okay. Yeah, I think I should start with the rocket. Strya. Last game I worked on, Double Action, one of the team members is from Strya. He's a riot. Okay. Yeah, let's talk about the rocket, but I'm going to talk about it slightly differently because I've already had a justification for root finding in general. So I'm just going to give one more example of the situation we can use root finding. Welcome back to Math for Game Developers. Today we have a crazy problem. We have a rocket that is out of control. Its thrusters are going all crazy. It's what are these called? The thrusters that are up here. I'm never gonna get this video recorded. Are they like maneuvering thrusters? Yeah, I'll call them, I guess they're actually called reaction control system, but I'll call them maneuvering thrusters. Because that makes more sense to somebody who has not studied rocket science. One of popular guest star stabilizers? I think a stabilizer is like a fin, like a physical... Okay, what am I doing? Oh. Okay. Yeah, I think the stabilizers are like the physical fins that turn, but that's good because the stabilizers will help this situation. I talk about them too. All right. Here we go. Welcome back to Math for Game Developers, where we're going to find another application for root finding. Here we have a rocket, and its stabilizers are all wonky, and its maneuvering thrusters are out of control, and it's thrusting at full throttle, and it's rotating in a really weird way, and it's headed toward this ground, and we have no idea where it's going to hit it. So this isn't a typical projectile motion problem. This is kind of a weird problem. There's drag involved, there's weird rotations and that sort of thing, but we still want to know what is going to be the intersection between this rocket and the ground. So this is another example of where you can take this problem and transform it into a route finding problem. So how are we going to do that? Actually, I drew this rocket trajectory 2 needs like this. Okay, this is the intersection we want to find. I'm going to draw it red because the rocket's going to blow up when it gets there. And how do we do that? We have one projectile, which I'm going to call f of x, and we have the ground, which I'm going to call g of x. Okay, and we want to know when f of x minus g of x is going to be equal to 0. When you subtract them, they're the same. So, if you subtract them and they're the same and they turn out to 0, that means they're the same. None of what I just said made sense, but I think you probably get the idea. If you subtract them and they're 0, that means they're the same. Okay, so if I make a new function h of x equals f of x minus g of x, then we can do root finding on this function h. And that's what we're going to do. And we're going to use a new method called Newton's method. And to explain how Newton's method works, I'm going to draw another graph here. Okay? Let's say that this is h right here. This is my h function. And we want to find this, this intersection point. All right, what is x when the value of h is 0? And we already have an estimate. We can just use a very simple estimate. We can pretend that this is a regular projectile motion, and we can pretend that this is a more or less flat surface, and we can get an estimate that way. And let's say our estimate is right here, x naught. Okay, so here's what I'm going to do. I'm going to find h of x naught. That's this point right here. H of x naught. And I'm going to find the slope, the tangent line at that point. And you can see that that tangent line intersects the x-axis at a point very close to where the actual function intersects the x-axis. So we can use this fact to improve our estimate of x. And here's how we're going to do it. Okay, we're gonna write a formula called point slope form, which you probably encountered in grade school somewhere. So the idea of this formula is we have a point, x naught, y naught, and we have a slope, m. And we can make an equation for this green line using this formula by just plugging in our slope and plugging in our point. Okay? So we can find the point, because we know that y naught is just going to be h at x naught. And we can find the slope because this function is going to have a derivative. Now here's a caveat. The function might not have a derivative. If it's crazy like this, if it's the ground, then we can approximate the derivative. And there are a few different methods of doing that. And the easiest method is just to take a point right here and take a point right there, evaluate the point, the slope at, evaluate the function at 2 points, and then use this line right here as the tangent. And that's called a secant. But for now, I'm just gonna, so that's pretty straightforward to do to find that secant. So for now, I'm just going to assume that we can either use that approximation or that h prime, the derivative of h, exists. Okay? So I'm going to rewrite this function now. This formula right here. Why did I write f? H x naught equals h prime. That is the derivative, or the tangent, the slope of the tangent line at the point x naught times x minus x naught. So that is the formula for this green line. Now we know that the intercept of the green line happens when y equals 0. So this is going to go to 0, and we're solving for x. We're trying to solve for x. So if I do solve for x, this is what I'm going to get. I'm going to get x equals x naught minus h at x naught over h prime at x naught. Now that is an approximation of x, not actually x. So I'm going to call it x1. So this line right here is going to get an intercept with the x-axis pretty close to x, to where x is. And I'm going to call that x1. And then I can do this over and over and over. Now I can use x1 as a new estimate, and it's a much better estimate. So I'm going to get, so if I do x1 minus, I'll even use a new color for it, x1 minus h at x1 over h prime at x1, then I get a new estimate, x2. And I can keep doing this forever, or until I get an acceptable estimate, an estimate that's within, I can use the same error calculation that I used, for example, in the bisection video, and to determine whether I'm now accurate enough. So this is Newton's method, and it converges to the answer that you want much, much faster than bisection method. And the reason for that is that every continuous function looks flat if you zoom in enough. If you zoom in to a very small space around the intersect of this function and the x-axis, then you can see the line looks almost straight at that point. And if it doesn't look straight, then keep zooming in and eventually it will look completely straight. And when it is completely straight, this tangent line is an exact estimate of that line. So the more you zoom in, the better your estimate gets. So Newton's method is a really strong method to use to estimate, to do root finding. But of course we have a few limitations, as always. And limitation number one is that you need a good first guess. And so as an example of what happens if you have a bad first guess, let's use this point as our first guess. It's not really far from that point, but you can see the tangent line at this blue point intersects the x-axis way far away from where we want to be. So this would make a bad first guess. So a lot of the times you can use, for example, bisection method to get a good first guess, and then you use Newton's method to improve your guess. The second requirement that you need is you need either it has a derivative, or you can get a good estimate of the derivative. I think that's about it. I think those are the two. Let me pause the recording of this video and make sure I'm not forgetting any requirements here. Any requirements for Newton's method? No, I think that's it. I think that's it. Newton's method is pretty powerful, but you need a first guess, and you need to be able to figure out the derivative. So, but while I'm here, I'm going to see what we're going to do. Well, no, I could just be ambiguous about it. Oops. What are we going to do next so I can talk? I always forget to look at what we're going to do next before I record the video, so I never remember what to talk about next. Yeah, I don't know if I've decided what we're going to... Probably interpolation, but I haven't decided. So, we'll just... And that's it. So, wait. What was I talking about this before I paused the video? What was I talking about? I remember. Okay. And that's all you need. Newton's method is a really powerful method. So no code section for this video. Next week, we are going to continue our exploration of numerical analysis. Probably, I think what's next on the docket is to go to interpolation and a few methods of doing that. So I'll see you next time. So then I have to cut out a few minutes there. Cut out. But I'll do that later. Editing video is boring. That all looks pretty good. And for once, it's actually possibly going to be under the time limit of 10 minutes. So that's good. Let's save this. Newton. Ah, good. We've done 2 videos. And it's almost 5. Thank you, Simon. Do I want to try another video? This one went really fast. It's funny because fixed point took forever. And then Newton took like, half an hour. Fixed point took 2.5 hours today. And then another 2 hours last week. And Newton, I think I did the whole thing in like half an hour. So, yeah. Yeah, no, but I think I want to go and eat dinner and that sort of thing. So I'm going to hang it up here. I'll do some editing the videos, put them up on the YouTubes, and we'll see you next week. I think I'm going to stream some during the week because I'm working on a game project, like a new game, and I might stream some of my Buoyancy. Let's look at that real quick. I might stream some of the coding of my new game, but it won't be anything like this. There won't be any math. Where was the Buoyancy? But I might run the stream then, so if you're around, starting maybe like in an hour on Monday, Tuesday, Wednesday, that sort of thing. Where was Buoyancy? How did I do Buoyancy? I don't think it was very technical what I did for Buoyancy. Yeah, it wasn't. So for Buoyancy, I just thought, okay, it's a bottle of air, and the air has a force on it like this is seaweed, right? And it traps, well, not air, but like it generates a gas that it traps inside like a cell inside of itself. And oh my god, this is so cute. I don't know if you guys can see this. Where's OBS? His back leg is twitching as he's asleep and he's dreaming. He's not doing it anymore. Yeah, so it's like a capsule of air inside a cell in the seaweed. And so the air is pushing up with pretty much a constant force. So that's all it's pretty much like buoyancy is just a constant force that's getting added into, oh, he's doing it now. That's getting added into the force equation. So it's not, I don't really think it's that interesting, the buoyancy. Okay. The twitching is probably hard to see on stream because it's twitching, obviously, so it's only very small, but anyway. Okay. So I don't know if buoyancy is that interesting. There are probably more interesting models of buoyancy. Oh, yeah. Yeah, you could definitely go deeper into it like that, and I didn't. I just wanted like a... In fact, my model for buoyancy is that the higher up you are in the chain, the more buoyant you are. And that's probably completely wrong, because... Actually, it's probably like the lower you are in the chain, the more the buoyancy force acts on you, because you have the buoyancy of all of the links above you pulling you up, right? But I did it this way because like I wanted it to kind of be stable and stay basically straight up. So I tried to pull the top ones up so that it would stay up. So it's not really lifelike, and you could probably do a density and volume and like difference between density and of water versus density of air sort of thing if you wanted to. Yeah, I don't know any fluid dynamics, so I don't know if I could really speak to that though. But for game purposes, you're probably just fine with just a force that, you know, a constant force in the up direction that looks right. Like, I don't know if there's really anything. Like, after you do all that math with the density and volume stuff, you're probably just going to get a constant force that pulls up. So, I read this source weird. Oh, do they? Okay. Well, oh, there's a Unity talk on it. Well, I'll go watch that then. Thanks for the pointer. So, okay. Oh, you know what? Do they do things like partially submerged buoyant objects that like you have to change the buoyancy depending on how much of the object is submerged? And also the source code of fear is available? That's interesting. I'll have to look that up. I'm gonna sign off and change this to, I'm gonna start typing in chat so that we can actually have a conversation that's not